Hey there, students. This is Mr. Tam here with an episode of Science to catch you up during this time where we're all essentially stuck at home, just so you don't fall behind and we can learn a little bit of science together. Now, today I'd like to continue off where we left off last time in discussing magnetism, and I'm going to also introduce to you guys today a little bit about what magnetic fields are. So let's go back to magnetism. So as you guys may or may not remember, we can classify substances under three specific categories: magnetic, ferromagnetic, and non-magnetic. Now, magnetic substances could automatically generate their own field, their own magnetic field. These are things like actual magnets with a north and south pole, as well as, we called it the rock, but essentially it's called a lodestone. Okay, and these lodestones or magnets on their own have the ability to generate a field in which either magnetic or ferromagnetic objects, when brought close enough, will be influenced by that field. Ferromagnetic, similar to magnetic, but it cannot generate their own field, but can be influenced by a magnet. And elements that fall under this category are found in the middle of the periodic table, and they are found in three varieties. One called nickel, one called cobalt, and one called iron. If we think of the French word fer, or iron, it'll help us definitely remember one of those three elements. They happen to be next to each other on the periodic table. Now, if a substance doesn't contain one of these three elements on their own, they cannot be influenced by a magnetic field. So, for example, a penny, which is made up of copper, will not be influenced by a magnet. But something that's made out of steel, for example, which is primarily iron, will definitely have some kind of effect when it's placed next to a magnet. And last but not least, we have non-magnetic field, or just non-magnetic, and these substances are not influenced in any way by magnets. So like I said earlier, metals that don't fall into one of those three categories don't get influenced by a magnet at all, and hence are non-magnetic. You have also things that are made out of rubber. You also have things that are made up of a very popular element, carbon. So things like wood and paper are all non-magnetic. So that's how we classify these substances, either by something being magnetic, which generates its own field, ferromagnetic, which can be influenced but doesn't generate its own field, and non-magnetic, which basically does absolutely nothing when placed next to magnets. Now, that being said, we're now going to explore something we call bar magnets. Now, bar magnets are the typical magnets that we use all the time. So they do have a north end and a south end. And when you place them next to each other, they'll do one of two things. They'll either move towards one another, which we call attracting. So if you have, for example, a north and a south coming together, they are attracting. Any other combination, be it south and south or north and north, will lead to those magnets pushing each other away. So this is an attraction. This is a repulsion. So these two repel one another. But for me, what's more important about this is the actual shape of the field it generates. Well, I like to think of the bar magnet as a sort of double rainbow. So I'm going to want to draw two lines on top like this, like an arch, and two lines on the bottom like this, like another double arch. And on the side, they also have a shape. It's like a prong, like of a fork. It branches outward. So this is the basic shape on how we draw bar magnets. If you look at the north and south here, every time you draw a line, there actually has to be a direction attached. Meaning, if I'm looking at the north end of the magnet and the south end, the north always goes towards the south. A little trick to help you guys remember this, of course, is during the winter, when it's really, really cold around here, we generally like to fly towards warmer countries like Mexico or the United States, namely Florida, or even in South America. So we go from the north in the winter towards the south. Again, that trick works on the edges as well. So we leave the north, so we draw arrows going away from the north and heading into the south, like so. So you're saying, Sir Tam, what happens if I were to place a compass next to these magnets? Well, an interesting thing happens when you place these compasses next to the magnet. Compasses are in fact mini magnets on their own. They actually like to stare at what makes them attracted to, they like to stare at what they like to stare at. So if you have a south end here, well, the north end wants to stare at that south end because it's comfortable there. It's the other way around. The south end wants to stare at the north end. It wants to be in the most comfortable position possible. Same thing here. If I were to place a compass down here, we would have the north end of the compass pointing to the south and the south end of the compass pointing to the north. Now, rather than writing N and S every single time, we actually sometimes just fill in the north end with a certain color. We actually just have to shade the north end in. So as you can see that I'm doing here, I'm shading in all the ends of the compasses that are the north. And it makes sense. And if you look very closely at the picture I drew above it, you could see that if all I do is put a circle around any one of these arrows, you're going to see that it mirrors essentially that north end of these compasses. So say, for example, this one right here, it'll mimic this one right here. So that's how you basically draw a magnetic field for any type of magnet. Similarly here, if I have a horseshoe magnet, it's the same thing. It goes from north to south and north to south. And we're going to draw two other rainbows here to go from north to south and north to south. If I wanted to draw a compass, I just place a circle around it and there's my compass. Nice and easy. But what happens if I were to draw a scenario that has north and south brought close to each other and they're attracting one another? Well, the attraction creates a sort of bridge. And this bridge could be illustrated by three lines like this. Does it have to be three lines? Absolutely not, but definitely makes our picture a lot clearer. So again, it goes from north all the way to south, north to south, and north to south. In the last scenario we're presented with, if I had north and north brought to each other, let's say, oops, sorry about that, north and north, well, they want to push each other away, which means that their fields similarly want to do so. So they want to go towards each other and then move away. They want to go towards each other, move away. They want to go towards each other and move away. Sort of as if there was an invisible barrier between the two. And again, the field lines don't change. In this case, because north are facing one another, the magnetic field lines want to go away from the north because it's really cold there. It goes away from the north and it heads towards, let's say, we extend this line towards the south. Extend this line right here, it goes towards the south. So that pretty much summarizes what you guys are responsible for when it comes to magnets and how to draw the magnetic fields. You can now give those pages a try that are in your workbook, pages 52 and 53. And if you haven't, if you did not get a chance to bring your materials home, I will send you a copy of the workbook and you could definitely work on that. So until the next episode, folks, take care of yourselves and all the ones around you. Make sure that you take good care of each other. Until next time, bye-bye.